This video is about IB Physics topic 4.1 oscillation, and we will talk about simple harmonic motion. One example of a simple harmonic motion is a mass spring oscillation. If I attach a mass to a spring and then I extend it by a bit and release it, from what we learned in topic 2.1, Hooke's law, there will be a restraining force exerted on the mass by the spring that want to pull the mass back to the equilibrium position. After passing through the equilibrium point, the mass will compress the spring, and later the spring will push the mass back to the equilibrium position. Therefore, we can expect that the mass will keep moving back and forth. Next thing is, what is the criteria for the motion to be a simple harmonic motion? There are two criteria. First, the acceleration is proportional to the displacement from the equilibrium position. Second, the acceleration is always towards the equilibrium position. Hence, from these two criteria, if we summarize them into a mathematical form, then the acceleration A is directly proportional to the negative x. The negative sign means the acceleration and displacement is always in the opposite direction. One last thing of the SHM is the property. One feature of a SHM is the period of the SHM is independent of the amplitude. That means no matter what the starting position of the mass is, it will still take the same time to finish a cycle. Then we need to learn the graph of a simple harmonic motion. For example, if we have a displacement time graph, as you can see here, the first thing we can know from the displacement time graph is the period, which is the horizontal distance between two crests. If we know the period, then we can also know the frequency, because frequency is the number of oscillation completed in 1 second. So we will have the equation F equal 1/t. For example, if the period is 0.1 second, then that means the system can complete 10 oscillations in 1 second, right? Then the frequency will be 10 Hz. In the IB exam, we will be asked to transform the displacement time graph into a velocity time graph. Then how can we do that? It is actually by considering the gradient of the displacement time graph, and then it will give the velocity of that particle. Now we consider point A, B, C, D as shown. At point A, the gradient is 0. Therefore, in the velocity time graph, we can mark the point the 0 velocity. At point B, it is the negative maximum gradient. Therefore, in the velocity time graph, we expect that point has a negative maximum velocity. And then at point C, the gradient is 0, therefore it has a 0 velocity. And at point D, that is a maximum positive gradient. So at the velocity time graph, there should be a maximum positive velocity. By repeating this method, we can get more points and connect all of them and get the velocity time graph. After learning how to transform a displacement time graph into a velocity time graph, now we learn how to transform a velocity time graph into an acceleration time graph. This can actually be done by considering the gradient, because the gradient of the velocity time graph will give the acceleration of that particle. Similarly, we consider the point A, B, C, D. At point A, the gradient is maximum negative gradient, so we'll have a maximum negative acceleration at that point. At point B, the gradient is 0, so we will have a 0 acceleration. While at point C, we have a maximum positive gradient, so we also have a maximum positive acceleration. While at point D, the gradient is 0, therefore the acceleration is also 0 at that point. By repeating the process, we can connect more points, and therefore we get the acceleration time graph. Then how can we transform a displacement time graph into an acceleration time graph? Since acceleration is proportional to the negative of displacement, therefore reflecting the displacement time graph along the time axis will give the acceleration time graph. As you can see here,